In this video, I'm going to take you through an example of a compound circuit problem. But before I begin, I want to remind you of just a few things. First, to get the most out of this video, you should try and work the problem along with me. And I would encourage you, as you're doing that, to go ahead and pause or rewind the video to help you follow along better. The other thing I want to remind you of is that these problems take patience. None of the steps individually are that tricky. What makes these problems challenging is just that there's a lot of steps and it takes some time to get through them. So with that, let's get started. The first thing I need to do is look for resistors that I can combine. On this diagram, R2 and R3 are going to be an easy pair to start with. Those two are in series with each other. I know they're in series because I could draw a line that starts at one side of R2 and goes through that one as well as R3 without encountering anywhere that the current splits. Since they're in series together, I just have to add those two together to get a new resistor that could replace them. I'm going to call that new resistor R23. So I have 15 ohms plus 10 ohms gives me 25. So the equivalent resistance of those two is 25 ohms. Once I've figured that out, I'm going to go ahead and redraw this circuit. Redrawing this does end up making it easier to keep track of some of the information you're going to need later. And when I redraw this, instead of drawing R2 and R3 separately, I'm going to replace them with just that single 25 ohm resistor, since that would act the same way. The next step for me is I'm going to combine R4 with that resistor I called R23. Those two are in parallel with each other. If I try to draw that line that goes through both of them, I have to go through a junction, a place where the current splits to go two different directions. When I've got resistors in parallel like that, I've got to do that 1 over stuff. So I'm going to call that new resistor R2, 3, and 4, since it's a combination of resistors 2, 3, and 4. And that's going to be equal to 1 over 25 ohms plus 1 over 12 ohms. I'm going to go ahead and just plug in 1 over 25 plus 1 over 12 on my calculator, which gives me 0.123. And I want to think of this as being 0.123 over 1 ohm, because that's going to make it easy to cross multiply and solve for what R234 has to be. So resistor 234 is going to be just 1 over 0.123, which is 8.1 ohms. Now that I've figured that out, I'm going to go ahead and redraw the circuit once more. Now all I've got left are two resistors that are in series with each other. So I can find the equivalent resistance of this entire circuit. Since these two resistors are in series, all I have to do is add them together. So I do 15 ohms plus 8.1 ohms to get 23.1 ohms as the equivalent resistance for this entire circuit. The next thing I'm going to do is find the total current through this circuit. When you're finding the total current, you have to use the voltage of the power supply, which on this problem is 48 volts. And whenever you're finding the total current, you have to use the equivalent resistance. So I put in 23.1 ohms. And then the formula for current is voltage over resistance. So I've got 48 volts over 23.1 ohms to get 2.1 amps. So there's my total current. At this point, I'm going to start labeling some information on the circuit diagrams that I've drawn. And I'm going to start working backwards through the problem. So first up, when you have a series circuit, the current is the same everywhere. So that means the current right here is 2.1 amps, and the current right here is 2.1 amps. The reason that matters is it's going to let me calculate the voltage on each of these resistors. So voltage is equal to I times R. And I have to do this once for each resistor. So I'm going to do 2.1 amps times 15 ohms to get 31.2 volts. And I'm going to do that same 2.1 amps times the resistance of the other guy, 8.1 ohms, to get 16.8 volts. At this point, it's a good idea to do a check to see if you're on the right track. Since right now I'm looking at a circuit that's entirely series, the voltage drop on each resistor should be the same as the voltage across the battery. So what that means is if I do 31.2 volts plus 16.8 volts, I should get the same voltage as the battery, which is 48. Since those add up, that tells me I'm probably on the right track so far. Now I'm going to go another step backwards. I'm going to look at this version of the circuit. Nothing about R1 has changed. So I'm going to go ahead and relabel those pieces of information again. Now I'm going to look at those two resistors in parallel. Whenever you have resistors in parallel, they have the same voltage. The voltage is the same across each branch. That voltage will be the same as the voltage on the single resistor I replaced them with. So since the resistor I replaced them with had 16.8 volts, that means that each of these also has 16.8 volts. Now that I know that, I can go ahead and find the current on each one. So I'm going to use once more that current is voltage divided by a resistance. So we really keep going back to the same formula and just rearranging it slightly differently. So for the resistor on top, I have 16.8 volts divided by 12 ohms is 1.4 amps. And for the resistor on the bottom, I'm going to do that same voltage, 16.8, divided by 25 ohms to get 0.67 amps. I'm going to do another check here. I like to do these checks in multiple places along the way to make sure I'm on the right track. Since the current into a junction has to equal the current coming out in parallel, that's another way of saying that if you add these two currents together, the current through each of these parallel resistors, you should get the same current as you had through the one you replaced them with. So down below, I had 2.1 amps going through that one resistor I replaced them with. So that if I add 1.4 plus 6.7, I also get 2.1 amps. So my answer checks out again. That tells me I probably haven't made any mistakes yet. And I am getting close to the end. So I'm going to go back one more step. And I'm going to go ahead and label the pieces I know again. And in fact, I can start filling in the table for some of these. So for example, for R1, I know right now that it has 2.1 amps and 31.2 volts. I also know about R4. I know it's got 1.4 amps and 16.8 volts. I can also fill in the equivalent resistance and the total current through this circuit. So now all that's left is to sort out R2 and R3. Since those two are in series together, they're going to have the same current. And their current will be the same as the current through the one I replaced them with. So each of these has 0.67 amps. And as long as the table's right here, I can go ahead and put them on there as well. So now I need to find the voltage on each of those two resistors. I'm going to use voltage equals I times R once more. So I have 0.67 amps times 15 ohms gives me 10.1 volts. And then if I do 0.67 amps times 10 ohms gives me 6.7 volts. And before I put these into the table, I'm going to do another check. The voltage, remember that the voltage drops across a series circuit should be the same as the total voltage across that circuit. I know the total voltage on the one resistor I replaced R2 and R3 with is 16.8. So that means those two voltages, 10.1 plus 6.7, if I add those together, I should get 16.8. So once again, my answer checks out. And I can go ahead and fill in these last few pieces of information. So these problems take some time, and they take some space to do. But remember, none of these steps are that hard. You just have to take your time with it.